When you heat lithium peroxide, it decomposes into lithium oxide. In contrast, sodium peroxide is stable at high temperatures. In this screencast, we'll explore why this difference in behaviour occurs. Since group 1 peroxides and oxides are both ionic solids, you can construct an enthalpy cycle for the decomposition. Two of the terms are the lattice enthalpies for the peroxide and for the oxide, with the oxide one negative, and the third term relates to the disproportionation of peroxide into oxygen and oxide. This step is independent of the metal and has a value of 845 kilojoules per mole. You can obtain estimates for the lattice enthalpies using the Capacitance equation. K is a constant, nu is the number of ions in the formula unit, Z plus and Z minus are positive integers giving the charges on the ions, and R plus and R minus are the ionic radii. K has the non-standard units picometers kilojoules per mole, and this allows you to use the ionic radii in picometers and gives the lattice energy in kilojoules per mole. The Capacitance equation gives a value for the lattice energy rather than the lattice enthalpy, but the difference between the two is relatively small and can be ignored. For lithium peroxide, the ionic radius for lithium plus is 76 picometers, and the thermochemical radius for peroxide is 167 picometers. Lithium peroxide has 3 ions in the formula unit, 2 lithium plus ions and 1 peroxide, and the charges on the ions are 1 and 2. Putting these values into the Capacitance equation gives a value for the lattice energy of 2660 kilojoules per mole. The calculation for lithium oxide is similar, with the exception of the ionic radius, which is 140 picometers for oxide. The Capacitance equation gives a value of the lattice energy of 3000 kilojoules per mole. The calculations for sodium peroxide and sodium oxide are also similar, though the sodium ion is larger with a cationic radius of 102 picometers. The Capacitance equation gives values of 2410 kilojoules per mole for sodium peroxide and 2680 kilojoules per mole for sodium oxide. For both lithium and sodium, the lattice energy of the oxide is greater than that of the peroxide. Both lattice energies decrease with the increasing size of the cation, but the lattice energy of the oxide decreases at the faster rate because of the smaller size of the anion. For lithium, you can use the enthalpy cycle to calculate the enthalpy change for decomposition. Putting the values in, we get a value for the enthalpy of decomposition of 505 kilojoules per mole. We do the same thing for sodium, and the corresponding value is 575 kilojoules per mole. For both lithium and sodium, the enthalpy change is endothermic, which makes sense since neither peroxide decomposes at room temperature. The decomposition temperature is when the Gibbs energy change is 0. The change in Gibbs energy depends on the change in enthalpy and the change in entropy, but since the entropy change is likely to be similar for both metals, and positive since the reaction involves half an equivalent of oxygen gas, the trend in Gibbs energies is given by the difference in the enthalpy change. The higher value of the enthalpy change for decomposition of sodium peroxide leads to a higher decomposition temperature for this compound. Decomposition of the peroxide to the oxide therefore becomes less favourable going down the group.